Hey guys, how's it going? Welcome to my channel, Just One More Linux. In this video here, we're going to be going over Cisco Enterprise Networking Security and Automation course, Chapter 6. Okay, we're going to be reviewing network address. So a lot of this chapter is very command heavy. A lot of the stuff that we're going to be looking at is going to actually be required to use packet tracer to really get a grasp on what we're doing, right? It's one of those things where when it's being explained, it sounds really, really complicated, but in practice, it's really not that complicated, and it's just way easier understood. You don't even necessarily have to do it yourself and follow along, but me doing it in packet tracer and walking you through the lab is really what's going to get your head around this if you're having trouble understanding exactly what NAT is. All right, so it's a short chapter when you take into consideration the fact that 6.4, oh sorry, I'm not on the window yet. Let's go here. When you take into consideration that 6.4, 6.5, and 6.6 are all actually basically packet tracer labs, right? There's content for these portions of the chapters, but they're really useless without having the lab open, and it's really just to guide you through the lab, okay? So really, we're going to just be going through 6.1, 6.2, and then it's going to be 6.3, and then this last part, 6.7. So it's just really three parts. 6.8 and 6.1 are, of course, just the introduction and then the quiz at the end. And there's also another packet tracer lab, which we will be doing in a separate video. All right, and the labs will also be in their own videos for this. So right now here in this video, we're going to cover the stuff in the content outside of these, or the stuff in the chapter outside of these, and then there'll be a separate video going over each lab, or I actually might do them all in one big video just because, well, no, I won't, because I'll do them all separately because I'd rather have people be able to search them if they're looking for just one. It'll be harder to name it if I do all of them and have it, show up in search results. So to start out here, let's take a look at what we're going to learn in this module. We're going to learn about NAT characteristics. We're going to learn about types of NAT, NAT advantages and disadvantages, Static NAT, Dynamic NAT, PAT or PAT, NAT64. Now, NAT stands for Network Address Translation. Now, I'll give you a hint right here. NAT64 actually has nothing to do with any of these other things right here, right? It's a similar name, but it's only similar in name. It's a very different thing, okay? We'll get into that when we get to that section though. So let's start out here at 6.1. All right, IPv4 private address space. So at this point, if you're looking into network address translation, I'm sure you've learned about network addresses, IPv4 addresses, and how we're pretty much been out of them. We've been out of them. If it weren't for things like NAT, it would be unusable at this point, and we would have had to been forced to completely transition to IPv6. Luckily, protocols like NAT are here to save the day. So, as you know, there are not enough public IPv4 addresses to assign a unique address to each device connected to the internet. Networks are commonly implemented using private IPv4 addresses as defined in RFC 1918. The range of addresses included in RFC 1918 are included in the following table, okay? And this right here are those ranges. We have A, which is 10 through 10.255.255.255, which is /8, okay? We have B, which is 172.16 through 172.31.255.255, and then we have C, which is the most common one, I think, probably every single device I've ever had on my home network, as many times as I've moved, has always been, I've always made it 192.168. and I think a lot of other people have as well. It's generally the default on most home routers. I'd be willing to bet that if it's not 192.168.172.1.6, you know what I mean? Anyways, these are the private ranges, right? These are not public. These private addresses are used with an organization or site to allow devices to communicate locally. However, because these addresses do not identify any single company or organization, private IPv4 addresses cannot be routed over the internet. To allow a device with a private address to access devices and resources outside of the network, the private address must be translated to a public address. All right, so that's where NAT comes in. NAT provides the translation of private addresses to public addresses, as shown in this figure. This follows the device with a private IPv4 address to access resources outside of their private network, such as those found on the internet. NAT combined with private IPv4 addresses has been the primary method of preserving public addresses. A single public address can be shared by hundreds, even thousands of devices, each configured with unique private address. Without NAT, the exhaustion of IPv4 address space would have occurred well before the year 2000. However, NAT has limitations and disadvantages which will be explored later in this module. The solution to the exhaustion of IPv4 address space and the limitations of NAT is the eventual transition to IPv6. All right? Now, if you've been learning about networking for pretty much any amount of time, you'll know that they've been talking about the transition to IPv6 forever. And of course, we use IPv6 today. A lot of people use IPv6. It's very common, but IPv4 is also still very common. I almost don't believe that we'll ever see it completely phased out. I don't know. I guess we'll see though. Who knows? Or, well, let's not make predictions. But still, they've been talking about the complete transition to IPv6 forever, and we're still here. Most of us use IPv4 for stuff. What is NAT? NAT has many uses, but its primary use is to conserve public address. It does this by allowing networks to use private addresses internally and providing translation to a public address only when needed. NAT has a perceived benefit of adding a degree of privacy and security to a network, because it hides internal addresses from outside networks. NAT-enabled routers can be configured with one or more valid public addresses. These public addresses are known as the NAT pool. When an internal device sends traffic out of the network, the NAT-enabled router translates the internal address of the device to a public address from the NAT pool. To outside devices, all traffic entering and exiting the network appears to have a public address from the provided pool of addresses. A NAT router typically operates at the border of a stub network. A stub network is one or more networks with a single connection to its neighboring network. One way in and one way out. In the example in the figure, R2 is a border router as seen from the ISP. R2 forms a stub network. All right. Take a look at that here. Here's our little small home style network. All right, you got a couple computers and a router, and there's only one way out of that network to the internet. Okay. When a device inside the stub network wants to communicate with a device outside of the network, the packet is forwarded to the border router. The border router performs the NAT process, translating the internal private address of the device to a public outside routable address. The connection to the ISP uses a private address or public address that is shared among customers. For the purpose of this module, a public address is shown. All right. How NAT works. Play this while I read here. In this example, PC1 with a private address 192.168.10.10 wants to communicate with an outside web server with public address 209.165.2011. All right, we're watching that happen right here. Play it one more time for you. Make it bigger. All right. Very simple. It's one of those things that sounds a little confusing when you hear it, and then when you watch it or actually do it, it's like, oh, okay. And that's a lot of stuff with networking in general, honestly. With all the acronyms and numbers, it sounds a lot more complicated than it is 99% of the time. NAT terminology. In NAT terminology, the inside network is the set of networks that is subject to translation. The outside network refers to all other networks. When using NAT, IPv4 addresses have different designations based on whether they are on the private network or on the public network, and whether the traffic is coming or going. NAT includes 4 types of addresses: inside local and global, and outside local and global addresses. Okay? When determining which type of address is used, it is important to remember that NAT terminology is always applied from the perspective of the device with the translated address. An inside address is the address of the device which is being translated by NAT. Okay? Outside address is the address of the destination device. Okay? So let's say our computer is on our network, okay, and it has an address 192 blah blah blah, and it's trying to ping a computer outside of the network. Okay, so far we have the example of our inside, we have our outside, and then that also uses the concept of local or global with respect to the address. All right, local address. A local address is any address that appears on the inside portion of the network. Global. A global address is an address that appears on the outside portion of the network. Okay? So that's like when you look at your computer, right? You put in IP config all, or you go to what's my IP, it differs, right? So like on your network, your address is going to be, the local address is going to be something like 192.168.0.101 or something, okay? And then your global IP address is going to be much different, okay? It's going to be a much different number. There's not really an example to give because they can be a lot of different things, right? As long as they're not in that private range. The terms inside and outside are combined with the terms local and global to refer to specific addresses. The NAT router, R2 in the figure, is the demarcation point between the inside and outside networks. R2 is configured with a pool of public addresses to assign to inside hosts. Refer to the network and NAT table in the figure for the following discussion of each of the NAT address types. All right, let's look at our little thing here. All right, and again, this makes it look way more complicated than it is. All right. Here, we can read more about those addresses. So our inside local, the address of the source as seen from the inside network. This is typically a private IPv4 address, such as 192.168.10.10. The address of the the inside global, the address of source as seen from the outside network. This is typically a globally routable address. When traffic from PC1 is sent to the web server at 209.165.201.1, R2 translates that to an inside global address. In this case, R2 changes the source address from 192.168.10.10, which was our inside local. It changes that to 209.165.200.206. In NAT terminology, the inside local address is 192.168.10.10, and it is translated to the inside global address of 209.165.200.226. The outside global address. The address of the destination as seen from the outside network. It is globally routable and assigned to a host on the internet. For example, the web server is reachable at IPv4 address 209.165.201.1. Most often, the outside local and outside global address are the same, okay? And then finally, outside local, the address of the destination as seen from inside network. In this example, PC1 sends traffic to the web server at the IPv4 address 209.165.2011. While uncommon, this address could be different than the globally routable address of destination. Okay? PC1 has an inside local address of 192.168.10.10 from the perspective of PC1. The web server has an outside address of 209.165.2011. When packets are sent from PC1 to the global address of the web server, the inside local address of PC1 is translated to 209.165.200.226, or the inside global. The address of the outside device is not typically translated because the address is usually a public address. Alright, and that's that. That's part 1. We're going to move on. We're going to skip a little test here. We're going to move on to 6.2.1, Static NAT. Alright, so now that you've learned about the basics of NAT and how it works, this topic will discuss the many versions of NAT that are available to you. Static NAT uses a one-to-one mapping of local and global addresses. These mappings are configured by the network administrator and remain constant. In the figure, R2 is configured with static mappings for the inside local address of server 1, PC2, and PC3. When these devices send traffic to the internet, their inside local addresses are translated to the configured inside global address. To outside networks, these devices appear to have public IPv4 addresses. Okay? And these don't change, right? So static NAT is particularly useful for web servers or devices that must have a constant address. It's really useful for when something needs to be reached, like a server serving a web page, like in this example, okay? Or using SSH, for example, okay? It's also useful for devices that must be accessible by authorized personnel when off-site, but not by the general public on the internet. For example, a network admin from PC4 can use SSH to gain access to the inside global address of server 1. R2 translates this inside global address to the inside local address and connects the session to server 1. Static NAT requires that enough public addresses are available to satisfy the total number of simultaneous user sessions. Now we have our second type of NAT, Dynamic NAT. And if you notice, this is very similar to a lot of other networking concepts, right? Static and dynamic. Dynamic NAT uses a pool of public addresses that assign them on a first-come, first-served basis. When an inside device requests access to an outside network, Dynamic NAT assigns an available address from the pool. All right? Very simple concept. Static, you're going to stay that way. Dynamic NAT, it gets assigned from a pool. In the figure, PC3 has accessed the internet using the first available address in the Dynamic NAT pool. The other addresses are still available for use. Similar to Static NAT, Dynamic NAT requires that enough public addresses are available to satisfy the total number of simultaneous user sessions. If you think about it, it's very similar to how DHCP works and static addressing, okay? So just how these our private addresses are configured, right? You might have computers on your network that have an address that doesn't change, and then you might have a pool for DHCP, okay? Very similar to that. In fact, it's extremely similar. Port address translation. Port address translation, or PAT, also known as NAT overload, maps multiple private IPv4 addresses to a single public IPv4 address or a few addresses. This is what most home routers do. The ISP assigns one address to the router, yet several members of the household can simultaneously access the internet. This is the most common form of NAT for both the home and enterprise. With PAT, or PAT, multiple addresses can be mapped to one or to a few addresses because each private address is also tracked by a port number. When a device initiates a TCP/IP session, it generates a TCP/UDP source port value, or specially assigned query ID for ICMP, to uniquely identify the session. When the NAT router receives a packet from the client, it uses its source port number to uniquely identify the specific NAT translation. PAT ensures that devices use a different TCP port number for each session with the server on the internet. When a response comes back from the server, the source port number, which becomes the destination port number on the return trip, determines to which device the router forwards the packets. The PAT process also validates that the incoming packets were requested, thus adding a degree of security to the session. Click play in the figure to view an animation of the PAT process. PAT adds unique source numbers to the inside global address to distinguish between transitions. Right, check this out. Don't mind. I'm gonna grab myself a drink here. Got my 2-liter of orange pop. Will you guys watch that one more time? Let's play it. Dry throat here. All right. Hopefully that's clear. Move on to the next session, next portion. As R2 processes each packet, it uses a port number 1331 and 1555. In this example, to identify the device from which the packet originated. The source address is the inside local address with the TCP/UDP assigned port number added. Destination address is the inside global address with the service port number added. In this example, the service port is 80, which is HTTP. For the source address, R2 translates the inside local address to an inside global address with the port number added. Destination address is not changed, but is now referred to as the outside global IPv4 address. When the web server replies, the path is reversed. Next available port. Right? In the previous example, the client port numbers 1331 and 1555 did not change at the NAT-enabled router. This is not a very likely scenario, because there's a good chance that these port numbers may have already been attached to other active sessions. PAT attempts to preserve the original source port. However, if the original source port is already used, PAT assigns the first available port numbers starting from the beginning of the appropriate port group. When there are more ports available, and there's more than one external address in the pool, PAT moves to the next address to try to allocate the original source port. This process continues until there are no more available ports or an external IPv4 address. Click play in the figure to view an animation of PAT operations. In this example, PAT has assigned the next available port, 1445, to the second host address. In this animation, the hosts have chosen the same port number of 1444. This is acceptable for the inside address, because the hosts have unique private IPv4 addresses. However, at the NAT router, the port numbers must be changed. Otherwise, packets from two different hosts would exit R2 with the same source address. This example assumes that the first 420 ports in the range are already in use, so the next available port number is 1445 is used. When packets are returned from the outside network, if the source port number was previously modified by the NAT-enabled router, the destination port number will now be changed back to the original port number by the NAT-enabled router. So here we have a NAT and PAT comparison. Being as we went through most of that, we just read this one-to-one comparison right here. NAT is a one-to-one mapping between inside local and inside global addresses. It only uses IPv4 address and translation process. A unique inside global address is required for each inside host accessing the outside network. With PAT, One inside global address can be mapped to many inside local addresses can be mapped to many inside local addresses. Users IPv4 addresses in TCP or UDP source port numbers in translation process. Uses IPv4 addresses in TCP or UDP source port numbers in the process. A single unique inside global address can be shared by many inside hosts accessing the network. All right. Packets without a layer or segment. What about IPv4 packets carrying other than a TCP or UDP segment? These packets do not contain a layer 4 port number. PAT translates most common protocols carried by IPv4 that do not use TCP or UDP as transport layer protocol. The most common of these is ICMPv4. Each of these types of protocols is handled differently by PAT. For example, ICMPv4 query messages, echo requests, and echo replies include a query ID. ICMPv4 uses the query ID to identify an echo request with its corresponding reply. The query ID is incremented with each echo request sent. PAT uses the query ID instead of a layer 4 port number. All right. 6.3.1. All right. We have advantages and disadvantages of NAT. All right. NAT solves the problem of not having enough IPv4 addresses, but it can also create other problems. This topic addresses advantages and disadvantages of NAT. NAT provides many benefits, including the following. NAT conserves the legally registered addressing scheme by allowing the privatization of internets. NAT conserves addresses through application port level multiplexing. With NAT overload, or PAT, internal hosts can share a single public address for all external communications. In this type of configuration, very few external addresses are required to support many internal hosts. NAT increases the flexibility of connections to the public network. Multiple pools, backup pools, and load balancing pools can be implemented to ensure reliable public network connections. NAT provides consistency for internal network addressing schemes. On a network not using private IPv4 addresses in NAT, changing the public address scheme requires the readdressing of all hosts on the network. The cost of readdressing hosts can be significant. NAT allows the existing private address scheme to remain while allowing for easy changes to a new public addressing scheme. This means an organization could change ISPs and not need to change any of its inside clients. Using RFC 1918 IPv4 addresses, NAT hides the IPv4 addresses of users in other devices. Some people consider this a security feature, however most experts agree that NAT does not provide security. A stateful firewall is what provides security on the edge of a network. Alright, and it's what allows us to all pretty much have very similar home network addressing schemes, right? I can almost guarantee that like 10 people on your street have a very similar addressing scheme, right? My neighbor probably has a 192.168.0.1, and I have a 192.168.0.1 as my computer. Examples like that, right? And even if it's not my neighbor, somebody else on my street has that. And it doesn't matter because NAT allows us to have, the ability to do that. Disadvantages of NAT. NAT does have drawbacks. The fact that hosts on the internet appear to communicate directly with the NAT-enabled device rather than the actual host inside the network can cause a number of issues. One disadvantage of using NAT is related to network performance, particularly for real-time protocols such as VoIP. NAT increases forwarding delays because the translation of each address within the packet headers takes time. The first packet is always process switched going through the slower path. The router must look at each packet to decide whether it needs translation. The router must alter the header and possibly alter the TCP or UDP headers. The IPv4 header checksum, along with the TCP or UDP checksum, must be recalculated each time a translation is made. Remaining packets go through the fast-switched path if a cache entry exists. Otherwise, they too are delayed. So that's one of the big disadvantages. It can slow down network performance significantly. The forwarding delays caused by NAT process become more of an issue as the pools of public addresses for ISPs become depleted. Many ISPs are still having to assign customers a private address instead of a public address. This means the customer's router translates the packet from its private address to the private IPv4 address of the ISP before forwarding the packet to another provider. The ISP will then perform NAT again, translating its private address to one of its limited number of public addresses. This process of 2 layers of NAT translation is known as carrier-grade NAT, or CGN. Another disadvantage of using NAT is that the end-to-end addressing is lost. This is known as end-to-end principle. Many internet protocols and applications depend on end-to-end addressing from the source to the destination. Some applications do not work with NAT. For example, some security applications, such as a digital signature, fail because the source address changes before reaching the destination. Applications that use physical addresses instead of a quantified domain name do not reach destinations that are translated across the NAT router. Sometimes, this problem can be avoided by implementing static NAT mappings. End-to-end IPv4 traceability is also lost. It becomes much more difficult to trace packets that undergo numerous packet address changes over multiple NAT hops, making troubleshooting challenging. Using NAT also complicates the use of tunneling protocols, such as IPsec or IPsec, because NAT modifies values in the headers, causing integrity checks to fail. Services that require the initiation of TCP connections from an outside network or stateless protocol, such as those using UDP, can be disrupted. Unless the NAT router has been configured to support such protocols, incoming packets cannot reach their destination. Some protocols can accommodate one instance of NAT between participating hosts, passive mode FTP for example, but fail when both systems are separated by the internet by NAT, from the internet by NAT. Okay, and then that's that for this portion. There's a little check your understanding, but skip that. You guys could do that on your own time. If you want, you can pause it and answer the questions. So as we talked about in the beginning of the video, close these up here so we get a better view. We also have a chapter specifically about static, dynamic, and PAT, right? But these are more about configuring those services, and they each have an accompanying lab for the text, right? So for example, configure static NAT. Here's that lab. In this lab, test access without NAT. Configure static NAT. Test access with NAT. And this just really goes over what you're doing in that lab in the basic commands, okay? And it's the same for both Dynamic NAT and PAT. So, for the sake of that, the accompanying text will be mentioned briefly in the videos for those labs, and we'll keep it to the labs for those portions of this chapter. So, after PAT, we can pick up at NAT 64, which is actually the last portion of this, right? We do also have a couple more labs in the end. We'll discuss those before I finish the video, but for now, let's move on to 6.7, which is NAT 64. And NAT 64 actually has pretty much nothing to do with NAT, right? NAT 64 is about translating IPv4 to IPv6, okay? So, because many networks use both IPv4 and IPv6, there needs to be a way to use IPv6 with NAT. This topic discusses how IPv6 can be integrated with NAT. IPv6 with a 128-bit address provides 340 undecillion addresses. Therefore, address space is not an issue. all right? And it's most definitely not. I should have looked it up for this video to include it, but I once read an article about how many devices each home would need to have to run out of IPv6 addressing space, and it's like insane. I think it's like in the millions per person. Each person could have millions of addresses on this planet, and we still wouldn't run out of IPv6 address space. I might be wrong in that number, but it's a crazy number, like an impossibly high number. We just can't run out. So, but then again, I guess they probably said that with IPv4 too. Although, who knows? So IPv6 was developed with the intention of making NAT for IPv4 with translation between public and private IPv4 addresses unnecessary. However, IPv6 does not include its own IPv6 private address space, unique local addresses. I'm sorry, read that wrong. However, IPv6 does include its own IPv6 private address space, called unique local addresses, or ULAs. All right? Unique local addresses are similar to RFC19 private addresses in IPv4, but have a different purpose. ULA addresses are meant for only local communications within a site. ULA addresses are not meant to provide additional IPv6 address space, nor to provide a level of security. IPv6 does not provide the protocol translation between IPv4. Sorry, I keep reading this wrong. IPv6 does provide for protocol translation between IPv4 and IPv6, and this is known as NAT64. Okay, so here's a brief description of NAT64. NAT for IPv6 is used in a much different context than NAT for IPv4. The varieties of NAT for IPv6 are used to transparently provide access between IPv6 and IPv4 only networks, as shown in the figure. It is not used as a form of private to global translation. Ideally, IPv6 should be run natively wherever possible. This means devices communicating with each other over IPv6 networks. However, to add in the move from IPv4 to IPv6, the IETF has developed several transition techniques to accommodate a variety of scenarios, including dual stack, tunneling, and translation. Dual stack is when the devices are running protocols associated with both IPv4 and IPv6. Tunneling for IPv6 is the process of encapsulating an IPv6 packet inside an IPv4 packet. This allows the packet to be transmitted over the IPv4 only network. Then NAT for IPv6 should not be used as a long-term strategy, but as a temporary mechanism to assist in the migration from IPv4 to IPv6. Over the years, there have been several types of NAT for IPv6, including Network Address Translation Protocol Translation, or NAT-PT, has been deprecated by IETF in favor of its replacement, NAT64. NAT64 is beyond the scope of this curriculum. All right, so basically that's all we need to know about NAT64 when it comes to this chapter. Okay, there's not really much to do with what we're actually talking about. So that's it. Okay, that is chapter 6, NAT, or NAT, or Network Address Translation. Okay, in 6.8 here, we have a few labs we can go over. One is about configuring NAT for IPv4, or they're actually both. I think one is actually to do with IRL things, and this one is just for packet tracer. Or did I have that backwards? Yeah, I have that backwards. This one is to do it with IRL things, and this is packet tracer. Okay, and then here we can go over what we learned in this module, and there's a little quiz at the end there, which we're going to skip. All right, so what did we learn? Right, we learned about NAT characteristics, the inside address and outside local addresses and global addresses. We learned about different types of NAT, NAT advantages and disadvantages, We learned about Static NAT, Dynamic NAT, PAT, and NAT64. All right. So if you want to review any of that, this is a video, so you can scroll it back. We're not going to review all the stuff we just read here. It's literally just the same stuff we all just learned in a short, neat little blurb. Hopefully you enjoyed this video. I hope you come and check out the packet tracer labs for this chapter, as a lot of them are pretty fun. For some reason, I actually personally find NAT really interesting, even though it's not that complicated. I don't know. I think I just have a lot more fun with the labs where we actually like trace packets and stuff, and I don't know. I had a good time with them. So check them out. Thank you for watching, and this has been just one more Linux. Have a good night.